Out there, at the very edge of our solar system, lurks a world so strange it forced astronomers to rewrite the textbooks. Eris, the dwarf planet, whose discovery in 2005 shattered our understanding of the cosmos. Imagine a frozen world, smaller than our moon, yet massive enough to upend centuries of planetary science overnight. This isn't just another speck of rock drifting in the darkness. Eris is a cosmic rebel, a celestial puzzle that defies explanation, and today we're diving deep into the 25 most baffling mysteries surrounding it. What makes this distant world so extraordinary? For starters, Eris shouldn't exist. Its discovery sent shockwaves through the scientific community, exposing flaws in our old definitions and sparking the infamous Pluto debate that still rages today. But the controversy is just the beginning. Eris is darker than coal, reflecting almost none of the sunlight that reaches it. Its surface is a frozen wasteland, yet somehow it's dense enough to suggest secrets hiding beneath the ice. And then there's its orbit, an erratic, tilted path that doesn't play by the rules of the solar system. What forces are at work here? What could possibly explain such defiance of gravity itself? This isn't just a story about a distant world. It's a journey into the unknown, a reminder that even in our own cosmic backyard, mysteries lurk in the shadows, waiting to be uncovered. From whispers of hidden oceans beneath its surface to the eerie possibility of unseen forces shaping its path, Eris challenges everything we think we know. And as we unravel these 25 enigmas, you'll begin to see this isn't just about a dwarf planet. It's about the untold stories of our universe, the questions that keep scientists awake at night, and the thrilling reality that we've only scratched the surface of what's out there. So buckle up. The deeper we go, the stranger it gets. Eris doesn't just drift through space, it defies it. While most planets and dwarf planets orbit the sun in relatively flat, circular paths, Eris dances to its own chaotic rhythm. Its orbit is wildly elliptical, swinging from a distant 8 billion miles away from the sun to a slightly closer 5 billion miles over the course of 557 years. But the real shocker, its path is tilted a staggering 44 degrees compared to the orderly plane of the solar system. Imagine a spinning top knocked sideways, wobbling unpredictably as it carves its own path through the void. This isn't just unusual, it's practically unheard of among its celestial neighbors. So how did Eris end up on this cosmic detour? One leading theory points to a violent past. Some scientists suspect Eris was once part of the inner Kuiper belt, a region packed with icy debris. Then, a close encounter with Neptune, or perhaps another massive object sent it hurtling outward, its orbit warped by the gravitational tug of war. Others propose an even wilder idea. Eris might be an interstellar interloper, a rogue world captured by our sun's gravity after drifting in from another star system. If true, that would make it a cosmic immigrant with secrets from far beyond our solar neighborhood. What's truly baffling is how stable its orbit remains despite the chaos. Most objects with such extreme paths would eventually be ejected or collide with something else. Yet Eris persists as if locked in some gravitational sweet spot. Could there be unseen forces at play? Some researchers speculate that an undiscovered, distant planet, often called Planet 9, might be shepherding Eris's path from the shadows. Others suggest its own immense density creates a gravitational anchor, resisting disruptions. Whatever the cause, one thing is clear: Eris isn't following the rules, and its rebellious orbit might hold clues to the solar system's most hidden mysteries. In the vast darkness of the outer solar system, Eris shines like a frozen beacon. Despite its immense distance from the sun, this dwarf planet reflects light with an intensity that rivals freshly fallen snow, making it one of the brightest objects beyond Neptune. But here's the puzzle: how can something so far from the sun's warmth gleam so brilliantly? The answer likely lies in its surface, a mirror-like landscape coated in methane ice. Picture a cosmic skating rink where temperatures plunge to nearly 400 degrees below zero, freezing methane into a crystalline shell so pristine it bounces sunlight back into space with astonishing efficiency. Yet this gleaming facade only deepens the mystery. Most icy worlds in the Kuiper belt are dull and dark, their surfaces weathered by eons of cosmic radiation. Eris, on the other hand, seems almost polished. One theory suggests its methane isn't just sitting there, it's constantly refreshing. Imagine geysers of gas erupting from below, freezing instantly in the void and dusting the surface like a fresh coat of glitter. This could mean Eris isn't the dead world we assumed. There might be enough internal heat, whether from radioactive decay or tidal forces, to keep its icy shell in a state of eerie renewal. Then there's the question of what's hiding beneath. Methane ice isn't just reflective, it's fragile. On Pluto, sunlight breaks it down over time, leaving behind a dark, reddish sludge. So why hasn't Eris suffered the same fate? Some researchers speculate its methane is mixed with other compounds, perhaps nitrogen or ethane, acting like a cosmic preservative. Others wonder if Eris's extreme seasons, caused by its tilted orbit, play a role. During its long, frigid winters, methane might condense into a protective layer, only to partially vaporize when it edges slightly closer to the sun. But the biggest twist, Eris's brightness defies expectations in another way. Its sheer reflectivity suggests the surface is smoother than most celestial bodies, raising the possibility of recent geological activity. On Earth, fresh ice means movement, glaciers shifting, volcanoes erupting beneath ice sheets. Could Eris, against all odds, still be geologically alive? The implications are staggering. A dynamic surface would hint at hidden energy sources, perhaps even a subsurface ocean insulated by layers of ice. If true, Eris isn't just a frozen relic, it's a world with secrets stirring beneath its dazzling shell, waiting to rewrite the story of how distant worlds evolve. When Eris was first discovered in 2005, astronomers made a startling announcement. This distant world wasn't just another icy rock in the Kuiper belt. It appeared to be larger than Pluto. The implications were seismic. If Eris outmatched Pluto in size, then either both were planets or neither was. The initial measurements, based on brightness and distance, suggested Eris was roughly 2,700 kilometers across, edging out Pluto's 2,370. Overnight, the solar system's hierarchy was thrown into chaos, but science has a way of correcting itself. By 2016, when NASA New Horizons mission provided precise measurements of Pluto's dimensions, astronomers turned back to Eris with sharper tools. Using stellar occultations, the moment when Eris passed in front of a distant star, they recalculated. The truth, Eris is smaller, but only just. At 2,326 kilometers in diameter, it's a near twin to Pluto in size. Yet this tiny difference sparked a colossal debate. How could two worlds so similar in stature provoke such cosmic controversy? The answer lies not in their size, but in their secrets. Despite being nearly identical in diameter, Eris is 27% more massive than Pluto. That extra heft means it's unimaginably dense for an icy world. Imagine compressing a glacier until it weighs like solid rock. What could possibly explain such density? One theory points to its composition. While Pluto is a mix of ice and rock, Eris might have a disproportionately large rocky core buried beneath its frozen shell. Some models suggest its core could make up nearly 80% of its total mass, unlike Pluto's more balanced structure. Then there's the puzzle of how such a dense world formed in the first place. Most Kuiper belt objects are loosely packed leftovers from the solar system's birth, more snowball than stone. Eris defies that logic. One possibility is that it endured a catastrophic collision early in its history, stripping away lighter materials and leaving behind a dense, compact remnant. Another idea, it might have formed much closer to the Sun, where rocky materials were abundant before being hurled outward into the frozen depths. But here's the twist: Eris's density isn't just a scientific curiosity. It could hold the key to understanding the solar system's turbulent youth. If Eris truly migrated from the inner solar system, its journey would paint a wilder, more violent picture of planetary billiards in the early days of our cosmic neighborhood. And if its core is as massive as suspected, it raises an even stranger question: what's happening beneath that icy surface? Could there be enough radioactive heat from those rocks to create pockets of liquid deep below? The debate over Eris's size may have settled, but the mysteries it unearthed are only getting deeper. Here's something that doesn't add up: Eris and Pluto are practically twins in size and composition. Yet while Pluto boasts a thin but detectable atmosphere, Eris appears to have none at all. How can two worlds so similar in so many ways be so fundamentally different in this crucial aspect? The answer might lie in the brutal physics of the outer solar system, where even small differences can have dramatic consequences. Take Pluto's atmosphere, for example. It's a wispy envelope of nitrogen, methane, and carbon monoxide, barely clinging to the surface. When Pluto swings closer to the Sun during its 248-year orbit, ices on its surface sublimate, transforming directly from solid to gas, and temporarily puff up this tenuous shroud. But as it retreats back into the deep freeze, much of that atmosphere collapses back onto the surface like frost settling on a winter window. Eris, though, never gets that chance. Its orbit keeps it perpetually in the solar system's freezer, with surface temperatures hovering around 400 degrees below zero. At that extreme cold, even volatile compounds like methane and nitrogen can't muster the energy to escape as gas. They stay locked in ice, leaving Eris exposed to the void. But there's another twist: Eris's reflectivity. That gleaming methane surface acts like a cosmic mirror, bouncing sunlight away before it can penetrate and warm the ices below. Pluto, by contrast, has darker patches where sunlight gets absorbed, creating just enough heat to trigger seasonal atmospheric changes. Without these dark regions, Eris remains in a state of suspended animation, its potential gases forever trapped in ice. Some researchers speculate that if Eris ever had an atmosphere, it's long since frozen solid, buried beneath millennia of fresh methane snowfall. Yet the mystery deepens when we consider Eris's density. That unusually massive core should, in theory, generate more internal heat through radioactive decay, enough perhaps to occasionally vent gases into space. So where are the telltale signs? One possibility is that any atmosphere Eris manages to produce is fleeting, collapsing back onto the surface almost immediately. Another, more tantalizing idea is that gases are escaping but invisibly. On Pluto, solar wind strips away atmospheric particles at a measurable rate. Eris, though, is so far from the Sun that this process might be achingly slow, leaving no detectable trace for our telescopes to catch. The most haunting question of all: what if Eris does have an atmosphere but we just can't see it? Right now, our best observations come from fleeting moments when Eris passes in front of distant stars, letting astronomers analyze how the starlight filters through or doesn't. These snapshots might miss temporary or patchy atmospheric pockets. Future missions armed with more sensitive instruments could reveal whispers of gas that current technology overlooks. Until then, the absence of an atmosphere remains one of Eris's most perplexing contradictions, a world built from the same blueprint as Pluto, yet playing by entirely different rules. Eris doesn't travel the solar system alone. It's accompanied by a silent, enigmatic partner. Dysnomia, Eris's lone moon, is more than just a cosmic sidekick. This tiny world, barely 150 kilometers across, holds clues to its parent planet's turbulent past. What makes Dysnomia so peculiar? For starters, its orbit is bizarrely tight and circular, skimming just 37,000 kilometers from Eris. That's closer than some satellites hover above Earth. Yet despite this snug distance, Dysnomia moves at a glacial pace, taking nearly 16 days to complete a single orbit. Most moons this close to their parent planet would race around in hours or days. So why is Dysnomia taking its sweet time? The answer might lie in how this moon formed. The leading theory suggests a cataclysmic collision, an ancient impact so violent it shattered part of Eris, launching debris into orbit that eventually coalesced into Dysnomia. This would explain the moon's composition, which appears eerily similar to Eris's own surface. But there's a problem. If Dysnomia were born from a giant impact, its orbit should be more elliptical, not the near-perfect circle we observe today. Some scientists propose tidal forces gradually smooth its path over eons, like cosmic sandpaper reshaping a rough edge. Others wonder if Dysnomia isn't a true moon at all, but a captured Kuiper belt object snatched by Eris's gravity in a chance encounter. Then there's Dysnomia's darkness. While Eris gleams with reflective methane ice, its moon is pitch black, absorbing almost all sunlight that touches it. This stark contrast hints at a surface stripped of volatile ices, perhaps scoured clean by radiation or collisions over billions of years. Even stranger, Dysnomia's orbit isn't just slow, it's perfectly synchronized with Eris's rotation, meaning the same face of the moon always points toward its parent planet. This tidal locking isn't unusual for moons, but combined with its other oddities, it paints a picture of a system that's been meticulously fine-tuned by time and gravity. But the real mystery is what Dysnomia reveals about Eris itself. The moon's sluggish orbit allows astronomers to calculate Eris's mass with precision, and that's how we know it's denser than Pluto. Without Dysnomia's gravitational tug, we might never have uncovered this critical difference. Some researchers even speculate that Dysnomia's presence stabilized Eris's axial tilt, acting like a counterweight to prevent its spin from wobbling chaotically over time. If true, this unassuming moon could be the reason Eris behaves so differently from other dwarf planets. The deeper we look, the more Dysnomia feels like a cosmic time capsule. Its orbit, composition, and even its darkness might hold records of the solar system's early chaos. Was Eris once part of a binary system, torn apart by some ancient gravitational upheaval? Could Dysnomia's surface still bear scars from the collision that birthed it? For now, these questions linger unanswered, but one thing is clear. This tiny moon is far more than a footnote in Eris's story. It's a silent witness to the violence and wonder of the outer solar system, and unlocking its secrets might just rewrite everything we thought we knew about how dwarf planets and their moons come to be. Eris's frozen surface hides more than just reflective methane ice. It's a canvas of unexplained scars and structures that defy easy explanation. High-resolution observations from telescopes like Hubble and ALMA have revealed patches of startling contrast where gleaming plains abruptly give way to shadowy depressions. Some regions appear fractured, as if the icy crust has been wrenched apart by some unseen force. These aren't your average impact craters or erosion patterns. They're anomalies that suggest Eris's history is far more turbulent than its stillness implies. Take the so-called dark basin, an irregular patch near Eris's equator that absorbs nearly all light. Unlike Pluto's dark regions, which are tinted reddish by Tholen's organic compounds cooked up by sunlight, this feature remains stubbornly black. One theory points to cryovolcanism, hidden geysers spewing a slurry of ice and carbon-rich sludge that freezes into a tar-like veneer. Another possibility, the basin might be a relic of an ancient collision where impact shockwaves vaporized surface ices, leaving behind a scorched, glassy residue. Either way, it's a glaring exception to Eris's otherwise mirror-like sheen. Then there's the ridge zone, a series of linear protrusions snaking across hundreds of kilometers. These formations bear an uncanny resemblance to Europa's chaos terrains, jumbled landscapes where subsurface oceans have fractured the ice above. Could Eris, too, harbor pockets of liquid beneath its shell? The sheer scale of these ridges hints at tectonic activity, but without the tidal forces that flex Europa's ice, what's driving the motion? Some models suggest Eris's dense core might still ooze residual heat, enough to creak and shift the overlying ice over millennia. Others speculate that seasonal changes triggered by its extreme axial tilt cause methane layers to expand and contract, buckling the surface like a frozen lake cracking under pressure. Perhaps most puzzling are the bright pits, circular depressions with walls that glow brighter than their surroundings. These aren't impact craters, their edges are too sharp, their floors too pristine. On Mars, similar features mark where buried ice has sublimated away, collapsing the ground above. But Eris is already ice cold. What's causing selective vaporization? One tantalizing possibility involves localized heat sources, perhaps radioactive minerals concentrated in the crust, creating just enough warmth to etch these eerie hollows. The deeper we look, the more Eris's surface feels like a cryptic ledger, recording events we're only beginning to decipher. Its features echo those seen on Pluto, Europa, and even distant Triton, yet they twist the rules just enough to keep scientists guessing. Is this a world frozen in time, or one quietly seething with hidden activity? Every strange marking whispers a different story, and until we send a probe to read them up close, Eris's surface will remain one of the solar system's most compelling enigmas. At the edge of the solar system, where sunlight is barely a whisper, Eris should be just another frozen relic, yet its chill is even deeper than physics predicts. With surface temperatures plunging to -400 degrees Fahrenheit, this dwarf planet defies standard thermal models. The math says an object this far from the sun, covered in highly reflective ice, ought to hover around -390 degrees. That 10-degree gap might seem trivial, but in the precision of planetary science, it's a screaming anomaly. So why is Eris unnaturally cold? The first clue lies in its dazzling sheen. That mirror-like methane surface doesn't just reflect sunlight, it rejects nearly all thermal energy, like a cosmic insulator bouncing heat back into space. But reflectivity alone can't explain the full discrepancy. Something else must be actively sapping warmth from Eris's already frigid environment. One theory points to sublimation, the process where ice skips the liquid phase and evaporates directly into gas. On Pluto, this creates a thin atmosphere while cooling the surface like evaporating sweat on skin. But Eris's extreme distance means even sublimation happens at a glacial pace, too slow to account for the missing heat. Then there's the wild card, Eris's interior. Most distant icy bodies are thought to be geologically dead, their cores long since cooled. But Eris's surprising density hints at a rocky heart packed with radioactive elements like uranium and potassium. These materials naturally decay, generating heat enough, you'd think, to warm the surface slightly. Yet the opposite seems true. Could Eris's core be too efficient at hoarding that warmth? Some models suggest its thick icy mantle acts like a thermos, trapping heat deep below where it can't reach the surface. If correct, Eris might harbor a toasty subterranean layer, forever hidden beneath its frozen crust. The plot thickens when we consider seasonal extremes. Eris's wildly tilted orbit creates millennia-long winters where parts of its surface never see sunlight. During these epochs, temperatures could plunge even lower than our current measurements, skewing averages. There's also the eerie possibility of cold traps, permanently shadowed regions where volatile compounds like nitrogen freeze into ultra-chilled deposits, dragging down the overall thermal profile. But the most radical explanation challenges our understanding of thermodynamics itself. A handful of researchers speculate that exotic ices on Eris's surface crystallized forms of methane or nitrogen arranged in unfamiliar molecular structures. might conduct heat unpredictably, essentially creating natural refrigeration. It's a concept borrowed from quantum materials on Earth, where certain compounds defy classical cooling laws. If true, Eris isn't just passively cold, it's running a cosmic air conditioner we don't fully understand. For now, the temperature gap remains one of Eris's most counterintuitive puzzles. Every explanation raises new questions. Is the surface actively cooling, or is the interior bizarrely insulated? Could unseen geological processes be redistributing heat in ways our models can't yet simulate? Answers might require a probe venturing to these distant reaches, armed with sensors to map thermal gradients in detail. Until then, Eris's unnatural chill stands as a reminder. Even the most basic laws of physics can twist into mysteries when tested at the frontiers of our solar system. Eris spins at a pace that defies expectations, taking nearly 26 hours to complete a single rotation. That's longer than a day on Earth and shockingly lethargic for a world its size. Most dwarf planets and Kuiper belt objects whirl much faster, some completing full turns in mere hours. So why is Eris dragging its feet? The answer might be locked in a gravitational dance with its moon Dysnomia, or written in the scars of ancient cosmic violence. Consider tidal locking first. Dysnomia's gravity exerts a subtle but constant pull on Eris, gradually sapping its rotational energy like an invisible brake. Over billions of years, this could have slowed Eris's spin to match Dysnomia's orbital period, a phenomenon called mutual tidal locking. Pluto and its largest moon Charon share this relationship, forever facing one another in a celestial waltz. But here's the catch. Dysnomia orbits Eris every 16 days, while Eris rotates every 26 hours. The numbers don't align neatly, suggesting tidal forces alone can't fully explain the sluggishness. Unless, of course, Dysnomia's orbit used to be tighter, and Eris's rotation is a relic of an earlier, more intense gravitational tug-of-war. Another possibility points to catastrophe. Imagine a colossal impact early in Eris's history, striking just off-center. Such a collision wouldn't just create Dysnomia, it could also send Eris spinning erratically like a top bumped off balance. Over time, friction within its icy mantle might have dampened that wild motion, leaving behind the gradual spin we see today. Computer simulations show this rotational braking effect is surprisingly common among icy worlds. The more massive the core, the more efficiently the planet's interior absorbs spin energy as heat. Given Eris's unusually dense structure, it could have bled rotational momentum far faster than lighter, puffier dwarf planets. Then there's the wild card, Eris's extreme seasons. Its highly tilted axis means one hemisphere basks in continuous sunlight for decades, while the other plunges into protracted darkness. This uneven heating could create atmospheric currents even in trace gases that act like atmospheric drag, subtly resisting rotation. On Mars, seasonal ice caps cause measurable changes in spin over centuries. For Eris, where temperature swings are even more exaggerated, the effect might be enough to explain those extra hours per day. The implications stretch beyond mere mechanics. A slow rotation means prolonged exposure to solar radiation on one side, potentially explaining why Eris's surface features vary so dramatically between hemispheres. It also affects internal dynamics. Less centrifugal force means less flattening at the poles and weaker convection currents in any subsurface ocean. If future probes discover that Eris's rotation is still slowing, it could hint at active geological processes beneath the ice, a hidden engine quietly rewriting the rules of motion at the solar system's edge. For now, the mystery of Eris's leisurely spin remains unresolved, a cosmic riddle scribbled in gravitational math and icy physics. Whether sculpted by its moon, forged in collision, or shaped by invisible atmospheric tides, this slow dance tells a story, one where time itself seems to stretch and warp in the frozen dark. And like so much about Eris, the truth may be stranger than any theory we've dared to imagine. Eris's surface gleams with an otherworldly sheen, thanks to a staggering abundance of methane ice. But this simple fact hides a conundrum that's left scientists scratching their heads. Methane, a volatile compound, should have evaporated into space billions of years ago under the faint sunlight at the edge of the solar system. Yet Eris wears its methane like a permanent frost, untouched by time. Compare this to Pluto, where methane sublimates into a wispy atmosphere, or Neptune's moon Triton, where geysers of nitrogen and methane erupt from beneath the ice. Eris's methane behaves differently, clinging stubbornly to its surface as if bound by some unseen force. So what's keeping this volatile compound locked in place? The first clue lies in temperature. Eris is colder than Pluto, hovering near -400 degrees, a frosty extreme where methane's volatility plummets. At these temperatures, the ice acts more like stone, resisting sublimation even over eons. But that's only part of the story. Pluto, though slightly warmer, also has methane, yet its surface darkens as sunlight breaks the molecules apart into reddish tholins. Eris, by contrast, remains blindingly bright, suggesting its methane isn't just surviving, it's being replenished. One theory points to cryovolcanism. Deep beneath Eris's icy crust, residual heat from radioactive decay might occasionally liquefy methane, sending sluggish plumes oozing to the surface where they freeze anew. This could explain the planet's uncanny reflectivity, like a self-repairing ice rink constantly resurfaced by hidden machinery. Another possibility involves Eris's chemical cocktail. Methane here might not exist in pure form, but instead mingle with nitrogen or ethane, forming a kind of antifreeze that stabilizes the ice. On Pluto, nitrogen dominates, creating a softer, more dynamic surface. Eris's blend could be fundamentally different, hardening into a fortress against sublimation. Then there's the seasonal wild card. Eris's extreme axial tilt, nearly 90 degrees, means its poles take turns, enduring centuries of uninterrupted sunlight or darkness. During the long winter, methane might condense into a thick global frost layer. When the sun finally grazes a hemisphere, only the topmost layer vaporizes, leaving the bulk intact. This slow motion cycle could preserve methane over geological timescales, like a glacier melting only at the edges, perhaps the most tantalizing idea. Eris's methane isn't native at all. Some researchers speculate it could be a relatively recent coating, delivered by comets or volatile-rich asteroids smashing into the surface. If true, Eris might be a cosmic ice museum, its exhibits preserved in a vacuum showcase. The methane mystery isn't just academic, it's a window into Eris's hidden activity. Whether fueled by underground reservoirs, chemical ingenuity, or celestial bombardments, this icy enigma proves that even in the solar system's silent outskirts, nothing is as inert as it seems. And as we piece together these clues, we're left with a haunting question. What else is lurking beneath that gleaming facade, waiting to rewrite the rules of planetary survival? Among Eris's gleaming expanses of methane ice lie stark, shadowy blemishes, irregular dark patches that stand out like ink stains on fresh snow. These regions absorb nearly all sunlight, a dramatic contrast to the dwarf planet's otherwise mirror-like surface. Some stretch hundreds of kilometers across, their edges jagged and uneven, as if something beneath the ice is seeping upward or the terrain itself is decaying. The puzzle isn't just their existence, it's their defiance of expectations. At Eris's distance, cosmic radiation should bleach organic compounds over time, leaving behind uniform reddish tints like those seen on Pluto. Yet these patches remain stubbornly black, a phenomenon with no clear parallel in the outer solar system. One leading theory points to cryovolcanic sludge. If Eris harbors even trace internal heat, methane mixed with heavier hydrocarbons like ethane or propane could ooze to the surface, forming viscous tar pits in the cold. As sunlight breaks down these compounds, they might polymerize into dark, complex organics. similar to the tholins found on Titan but far denser. Another possibility suggests ancient impacts excavated deep-buried carbon-rich material, scattering it across the ice like cosmic graffiti. On Pluto, similar dark regions coincide with crater sites, but Eris's patches show no obvious correlation to impact basins, raising questions about their origins. The most provocative hypothesis involves radiation chemistry. Eris's slow rotation exposes certain regions to prolonged cosmic rays, enough to shatter methane molecules into carbon chains and hydrogen gas. Over millennia, this could create a thin layer of graphite-like carbon, darkening the surface like a pencil smudge on glass. Intriguingly, lab simulations show methane ice bombarded by radiation does form dark residues but never as pitch black as Eris's patches. Something else must be amplifying the effect, perhaps interactions with nitrogen or sulfur compounds lurking in the ice. Then there's the wild card, seasonal shadowing. Eris's extreme axial tilt creates polar night spans lasting centuries, allowing frost to build into thick, insulating layers. In these sunless voids, even trace atmospheric gases might condense into exotic ices, nitrogen mixed with carbon monoxide or acetylene, that darken under radiation without the bleaching effect of sunlight. When the pole finally tilts toward the sun, these ices could sublimate unevenly, leaving behind tar-like residues in the coldest microclimates. What makes these dark zones truly perplexing is their persistence. On other icy worlds, dark material eventually blends or erodes, yet Eris's patches remain sharp-edged as if actively maintained. Could underground reservoirs be seeping fresh hydrocarbons to the surface, or is some unseen geological process continually refreshing these stains? Until a probe arrives to scrutinize them up close, these Inkai puzzles will remain, a silent challenge to our understanding of how surfaces evolve in the solar system's frozen fringe. Eris doesn't just orbit at the edge of the solar system, it feels like an intruder there, a cosmic misfit with origins shrouded in violent uncertainty. The prevailing theory suggests it formed alongside other Kuiper belt objects, a frozen relic of the solar system's birth, but too many pieces of Eris's puzzle refuse to fit. Its extreme density, its tilted orbit, even its gleaming methane coat, all hint at a past far more tumultuous than its icy neighbors. Could this dwarf planet have been hurled into the darkness from somewhere closer to the sun, or is it a rare survivor of the Kuiper belt's primordial chaos? The case for a local origin starts with composition. Eris's surface mirrors other distant worlds like Pluto and Makemake, rich in methane and nitrogen ices. This suggests it condensed from the same frigid reservoir of material, a frozen sibling born in the outer solar system's chill, but that's where the similarities end. Most Kuiper belt objects are loosely packed, their structures more snowball than stone. Eris, with its startling density, behaves like a rocky planet wrapped in an icy disguise. One explanation, it might have formed during the solar system's infancy, when the Kuiper belt was denser and richer in heavy elements. Over time, collisions could have stripped away lighter materials, leaving behind a compact, dense core like a cosmic blacksmith forging a cannonball from scrap metal. Yet there's a competing narrative, one that paints Eris as a wanderer. Its wild, tilted orbit is the first red flag. Most objects in the Kuiper belt move in relatively flat, circular paths, like marbles rolling on a table. Eris, by contrast, orbits at a steep 44-degree angle, as if knocked askew by some ancient gravitational kick. Computer simulations show this could happen if Neptune's migration, a chaotic shuffle billions of years ago, flung Eris outward like a slingshot. But even that doesn't fully explain its peculiar density. Some scientists speculate Eris might have originated in the inner solar system, where rocky materials were abundant before being ejected by a close encounter with Jupiter or Saturn. The plot thickens when we consider Eris's moon, Dysnomia. Moons born from collisions like Earth's moon typically have compositions matching their parent bodies. Dysnomia's darkness and tight orbit suggest a violent past, but its precise origins remain murky. If Eris were a captured interloper, Dysnomia might be a tag-along from its original home, or debris from a catastrophic encounter during its exile. Alternatively, if Eris formed locally, Dysnomia could be a fragment from a collision that also compacted Eris's core, explaining its unnatural heft. The most tantalizing clue lies in Eris's surface chemistry. Its methane lacks the reddish tholins seen on Pluto, hinting at some process actively renewing the ice. If Eris migrated from warmer climes, its methane might be a later addition, frozen onto its surface after the journey. Or perhaps internal heat left over from its violent ejection still drives cryovolcanic resurfacing today. The debate over Eris's origins isn't just academic. If it truly migrated, its composition could preserve secrets of the inner solar system's early days, frozen in time. If it formed in place, its density challenges our models of how icy worlds evolve. Either way, Eris stands as a testament to the solar system's turbulent youth, a reminder that the cosmos rarely follows tidy rules, and until we send a mission to its frozen shores, this dwarf planet's birth story will remain one of the Kuiper Belt's most gripping unsolved mysteries. Eris's surface tells a story, but it's a story with pages missing. For a world that spent billions of years in the chaotic Kuiper Belt, it should be pockmarked with craters, each one a scar from ancient collisions. Yet high-resolution observations reveal a landscape suspiciously smooth, as if something has been quietly erasing the evidence. This isn't just odd, it's unprecedented for an object of Eris's size. Even Pluto, its closest sibling, wears its cratered history plainly. So why does Eris get to play by different rules? One compelling answer lies beneath the ice. Cryovolcanism, the eruption of water, methane, or ammonia instead of molten rock, could act as nature's eraser. Imagine geysers of slushy ice bursting through fissures, spreading fresh layers that bury old impacts like snowfall covering footprints. On Neptune's moon, Triton, similar activity creates vast, wrinkle-free plains. But there's a catch. Triton has tidal heating from Neptune's gravity to power its eruptions. Eris, with no giant planet nearby, would need another engine. That's where its dense core comes in. The radioactive decay of heavy elements like uranium and thorium could generate just enough heat to occasionally melt subsurface pockets, forcing sludge upward to resurface the terrain. Even a trickle of this activity over eons could explain the scarcity of craters. Then there's the methane factor. Eris's gleaming coat isn't static. Sunlight, though faint, constantly chips away at exposed methane molecules, breaking them down into darker compounds. But instead of accumulating, these byproducts seem to vanish, suggesting the ice sheet is renewing itself. Some models propose seasonal snowfall, where methane vapor migrates from warmer to colder regions, frosting the surface in a slow-motion cycle. Over millennia, this process could fill in small craters entirely, like a self-leveling cake glaze, but the most tantalizing clue comes from Eris's density. That unusually massive core might not just generate heat, it could also make the planet more geologically resilient. When impacts strike, Eris's stiff interior might absorb shocks differently than softer, icier worlds, causing craters to sag and smooth out faster. Think of dropping a rock into fresh cement versus wet sand. The heavier mixture resists forming deep pits. This could mean Eris's surface isn't just being resurfaced, it's actively resisting scars in the first place. The implications are staggering. If Eris is still geologically alive, however faintly, it joins an elite club of worlds like Europa and Enceladus, places where internal activity defies the cold grip of space. But unlike those moons, Eris has no tidal forces to explain its vigor. It's running on its own mysterious clock, a testament to the hidden energies lurking in even the darkest corners of our solar system. And until we land a probe on its unnervingly smooth plains, this craterless enigma will keep challenging our assumptions about what distant worlds are capable of. When astronomers point their spectrometers at Eris, the data that comes back tells a story stranger than fiction. This distant world doesn't just reflect sunlight, it filters it through a cosmic prism, leaving behind spectral fingerprints that refuse to match any known material in the outer solar system. The anomalies show up most starkly in infrared wavelengths, where Eris's surface absorbs specific frequencies of light in ways that defy simple explanations. These aren't just minor discrepancies, they're glaring deviations that hint at chemistry we've never seen before, unfolding on a world where the rules seem rewritten. Take the methane, for instance. On Pluto and Triton, methane ice leaves clean, predictable absorption lines in the spectrum, like barcodes revealing its presence. But Eris's methane signals are smeared, as if something is distorting the molecules at a fundamental level. One theory suggests the methane here isn't pure but trapped in a lattice with nitrogen or other ices, altering how it interacts with light. Picture a diamond with impurities that change its color, except in this case, the impurities might be exotic compounds formed under pressures and temperatures we can't yet replicate in labs. Then there's the baffling absence of certain signatures. Most icy bodies in the Kuiper belt show traces of water ice, but Eris's spectrum stubbornly resists revealing it clearly. Either the water is buried too deep for our instruments to detect, or it's chemically bound in ways that render it invisible. Some researchers propose that Eris's surface is dominated by a thick layer of methane clathrates, crystalline structures where methane molecules are caged inside water ice. These bizarre materials found in Earth's deep oceans could explain both the missing water signals and the odd methane behavior. If true, Eris's crust might resemble a frozen, cosmic honeycomb with gases trapped in icy prisons. But the real head-scratchers are the unidentified absorption bands, mysterious dips in the spectrum that correspond to no known compound. On other worlds, such features often point to complex organics or minerals. Yet Eris's dark patches, which should harbor these substances, don't align neatly with the spectral anomalies. One radical hypothesis suggests the culprit could be irradiated plastics, long-chain hydrocarbons polymerized by relentless cosmic rays into something akin to interstellar polyethylene. Another idea floats the possibility of sulfur compounds cycled through hypothetical cryovolcanic vents, staining the ice in ways we've never observed elsewhere. The plot thickens when we consider what isn't there. Eris's spectrum shows no evidence of carbon monoxide or nitrogen ices, both common on Pluto and Triton. Their absence implies either a formation history devoid of these volatiles or some process actively removing them. Could Eris's interior heat, if it exists, be cracking these molecules apart and sequestering the remnants underground? Or does its extreme orbit prevent these ices from stabilizing on the surface? Every unexplained line in Eris's spectral signature is a breadcrumb leading toward bigger questions. Are we looking at chemistry unique to this world, shaped by conditions unimaginable on Earth? Or is Eris a time capsule preserving primordial substances that vanished everywhere else? Until we can sample its surface directly, these spectral riddles will linger, a reminder that even light, our most trusted messenger from the cosmos, can carry mysteries we're not yet equipped to decode. Eris's gravitational pull might seem insignificant at first glance. After all, it's just a dwarf planet. But out in the scattered disk, that icy no-man's land beyond Neptune, this tiny world wields surprising influence. Its gravity stretches far enough to nudge other objects into strange orbits, creating a ripple effect that scientists are only beginning to map. Like an invisible hand in the darkness, Eris quietly reshapes the paths of its neighbors, leaving behind a cosmic fingerprint we're still deciphering. Take the scattered disk population, a group of icy bodies with orbits even wilder than Eris's own. These objects don't circle the sun neatly. they loop and dive at extreme angles as if tossed by some ancient celestial collision. Recent simulations suggest Eris might be partly responsible. Its gravitational tugs, combined with Neptune's, could have acted like a slingshot, flinging smaller objects outward while warping their trajectories into those erratic paths we see today. It's a delicate dance of forces. Neptune's gravity sends them careening toward the outer solar system, and Eris's pull adds the final twist, locking them into orbits tilted beyond the norm. But here's where it gets intriguing. Some of these scattered disk objects cluster in ways that shouldn't happen by chance alone. Their orbital angles and distances hint at gravitational resonances, points where Eris's repeated tugs synchronize with their orbits like a metronome keeping time. This isn't just theoretical. One object in particular, 2113 UZ, shares an orbital rhythm with Eris that's mathematically too precise to ignore. Every time Eris completes a certain number of orbits, this distant cousin seems to answer with a gravitational echo. The odds of this happening randomly are astronomically low, suggesting Eris's influence is active, not accidental. Then there's the enigma of Eris's own stability. Despite its extreme orbit, it doesn't wander aimlessly like many scattered disk objects. Instead, it's locked in a gravitational balancing act. Neptune's pull prevents it from drifting too far inward, while Eris's hefty mass and Dysnomia's presence anchor it against further disruption. This equilibrium raises a tantalizing question. Could Eris be acting as a shepherd, herding other objects into similar stable pockets? If so, it might explain why some regions of the scattered disk feel emptier than they should, as if something has cleared the chaos and imposed order. The ultimate mystery lies in what we can't yet see. Computer models hint that Eris's gravity might be masking even more distant objects, worlds too dim for our telescopes to spot. Just as Pluto's discovery led us to the Kuiper belt, Eris's gravitational whispers could point to hidden giants lurking in the dark. Some researchers speculate that Eris itself might once have been part of a binary system, its twin since lost to the void but leaving behind subtle traces in the orbits of nearby bodies. Every gravitational nudge, every synchronized orbit tells a story, one where Eris isn't just a passive relic but an active architect of the solar system's frozen fringe. As we piece together these clues, one thing becomes clear. In the silent vastness of the scattered disk, Eris's pull is far stronger than its size suggests, and the echoes of its influence might rewrite our understanding of how tiny worlds shape the cosmos. Eris didn't just earn its name by chance, it was a declaration. In Greek mythology, Eris was the goddess of chaos and strife, the troublemaker who famously tossed the golden apple inscribed "to the fairest" into a divine gathering, sparking the conflict that led to the Trojan War. When astronomers chose this name in 2006, they weren't merely picking from a list, they were making a statement. This dwarf planet had already upended the solar system's order, igniting fiery debates about what defines a planet and ultimately leading to Pluto's demotion. The cosmic irony, just as the mythological Eris sowed discord among the gods, her namesake celestial body threw the astronomical community into turmoil, forcing a reckoning with centuries of planetary definitions. The naming itself was a masterstroke of symbolism. Before its official designation, Eris bore the provisional label 2003 UB313, a sterile identifier for something so disruptive. Its discoverers, led by Mike Brown, knew they'd found something extraordinary, a world massive enough to challenge Pluto's status. By invoking the goddess of discord, they underscored the scientific upheaval it represented. The International Astronomical Union, tasked with approving the name, couldn't have missed the message. Here was a celestial rebel, a world whose very existence demanded the cosmos be resorted. But the parallels run deeper than mere controversy. In myth, Eris operated from the shadows, her influence indirect but seismic. The dwarf planet mirrors this perfectly. It wasn't Eris's size alone that forced Pluto's reclassification. It was the realization that if Pluto qualified as a planet, so too must Eris, and likely dozens of other Kuiper belt objects. The goddess's apple exposed divisions among the Olympians. The dwarf planet exposed flaws in our celestial taxonomy. Both forced a confrontation with uncomfortable truths. For the Greeks, the pettiness of their deities; for astronomers, the arbitrariness of old definitions. There's a darker edge to the connection, too. Ancient Greeks feared Eris's capriciousness, blaming her for wars and famines. In a way, modern science harbors its own unease toward the dwarf planet, not out of superstition, but because its discovery revealed how little we truly understand about the solar system's boundaries. Eris the goddess thrived in chaos. Eris the world thrives in the unknown, a reminder that even our most precise models have blind spots, perhaps the most poetic twist. In myth, Eris had a counterpart, Harmonia, the goddess of harmony. Yet no celestial body bears that name beyond the asteroid 2058 Harmonia. The cosmos, it seems, favors discord over order, upheaval over stasis. And as long as Eris spins in the darkness, its name will stand as a testament to the beautiful, messy process of scientific discovery, where every answer sparks new questions and every truth unsettles the status quo. The search for Planet X has haunted astronomers for over a century, a phantom world lurking in the solar system's outer dark, its gravitational fingerprints the only evidence of its existence. And right in the thick of this cosmic detective story sits Eris, its peculiar orbit raising provocative questions. Could this dwarf planet be part of something bigger? A hidden network of worlds, perhaps even a trail leading to the elusive Planet 9. The clues lie in the math. Eris's wild, tilted path is the first breadcrumb. Most distant objects in the Kuiper belt cluster in orbits aligned with the solar system's plane, except for a handful of outliers, Eris included. Their trajectories seem to point toward an unseen shepherd, something massive enough to tug them into sync. Enter Planet X, a hypothetical world up to 10 times Earth's mass, lurking 20 times farther out than Neptune. Computer simulations show such a planet could explain Eris's orbital quirks, its gravity sculpting the dwarf planet's path like an invisible hand guiding a spinning top. But here's where it gets stranger. Eris isn't alone in its defiance. Several extreme trans-Neptunian objects share similar orbital tilts and eccentricities, as if they're all dancing to the same gravitational tune. Some researchers argue this isn't coincidence, it's evidence of Planet X's influence. In their models, Eris and its scattered kin act like celestial breadcrumbs, marking the trail to something far larger hiding in the shadows. Yet skeptics counter with another explanation: cosmic chance. The outer solar system is a graveyard of ancient collisions, and Eris's odd orbit might simply be debris from a primordial smash-up. Its density supports this. Perhaps it's the shattered core of a once larger world, sent careening by the violence that birthed it. If true, Planet X becomes unnecessary, and Eris's path is just a scar from the solar system's violent youth. The debate hinges on what we can't yet see. Current telescopes struggle to spot cold, distant objects like Planet X, leaving astronomers to hunt for indirect clues. Eris, as one of the brightest denizens of the Kuiper belt, offers a critical test case. If future observations reveal more objects clustered in similar orbits, the case for Planet X strengthens. If not, Eris's rebellion might be a solo act, a rogue world refusing to conform. One thing's certain: Eris's role in this mystery is far from settled. Whether it's a pawn in Planet X's gravitational game or a lone maverick writing its own rules, this icy enigma keeps pulling us deeper into the dark, where the answers and perhaps new questions wait to be uncovered. Eris's shimmering surface hides a peculiar secret. It doesn't shine with consistent brilliance. Over years of observations, astronomers have recorded subtle but unmistakable shifts in its reflectivity, as if the dwarf planet itself is breathing, dimming and brightening in rhythms we don't yet understand. These albedo changes, up to 10% in some measurements, defy expectations for a world so far from the sun's warmth. On dead, frozen worlds, brightness should be static, locked in ice for eons. Yet Eris pulses like a slow, distant heartbeat, and the reasons might rewrite what we know about distant icy bodies. Seasonal shifts top the list of suspects. Thanks to Eris's extreme axial tilt, its poles take turns enduring centuries of relentless sunlight or unbroken darkness. During the long polar summer, methane ice near the pole might warm just enough to vaporize slightly, lofting gas to the opposite hemisphere where it refreezes as fresh frost. This slow migration could brighten one side while the other darkens under accumulated radiation, darkened tholins. Pluto undergoes similar changes, but on a more exaggerated scale. Its thin atmosphere shuttles nitrogen and methane across the surface with its seasons. Eris, colder and airless, would operate in ultra-slow motion, its cycles playing out over millennia rather than decades. Yet there's a wrinkle in this theory. Unlike Pluto, where seasonal changes are predictable, Eris's brightness fluctuations don't always align neatly with its orbital position. Some darkening events occur unexpectedly, as if triggered by something deeper. This raises the tantalizing possibility of cryovolcanic resurfacing, buried geysers erupting sporadically to paint fresh ice across patches of terrain. On Neptune's moon Triton, similar plumes of nitrogen gas and dust streak the surface, leaving bright scars. If Eris harbors even trace internal heat, its dense core could occasionally melt subsurface pockets, forcing slushy eruptions that refresh the ice in localized bursts. The most puzzling variations, though, are the short-term spikes, sudden brightening events lasting just months. These can't be explained by seasons or geology alone. One radical hypothesis points to cosmic impacts. Imagine a rogue comet rich in fresh methane ice, slamming into Eris and scattering reflective debris across its surface. Another idea involves solar flares, rare but powerful bursts of radiation that might briefly ionize surface ices, altering their reflective properties. Or perhaps Eris's orbit carries it through faint dust clouds in the Kuiper belt, with passing grains acting like microscopic mirrors, temporarily boosting its shine. The implications stretch beyond academic curiosity. If Eris's brightness changes stem from active processes, it joins an elite club of living worlds like Europa and Enceladus, where hidden energy reshapes the surface against all odds. But if the shifts are primarily external, cosmic, weather or impact debris, they could reveal unseen dynamics in the outer solar system's environment. Every flicker of Eris's light is a cipher awaiting decoding, a signal from the dark that might teach us not just about one dwarf planet, but about the forces sculpting the frozen frontier of our cosmic neighborhood. Eris's chemistry holds another stark contradiction. While most icy worlds in the Kuiper belt carry traces of volatile compounds like carbon monoxide and nitrogen, Eris's surface appears stripped of these materials. It's as if someone meticulously erased them from the recipe, leaving behind only methane as the dominant volatile. This absence isn't just curious, it's a scientific red flag, suggesting Eris's history unfolded under conditions radically different from its neighbors. Take Pluto as the obvious comparison. Its surface boasts nitrogen glaciers, carbon monoxide deposits, and even traces of acetylene, all frozen relics of the solar system's primordial soup. These volatiles should be commonplace among similar-sized worlds, yet Eris's spectral data shows none of them. The simplest explanation points to temperature. Eris's orbit keeps it farther from the Sun than Pluto for most of its long year, with surface conditions hovering near -400 degrees, cold enough to freeze nitrogen into immobility. But here's the catch. Pluto's most distant stretches are only slightly warmer, yet it still retains these compounds. Temperature alone can't explain the discrepancy. Another possibility involves Eris's formation zone. Volatiles like nitrogen and carbon monoxide are fragile. they condense easily in the outer solar system's chill but struggle to survive closer to the Sun's warmth. If Eris originated nearer to Neptune before being scattered outward, much of its original volatile inventory might have vaporized during this migration, leaving behind only the hardier methane. This would also explain Eris's high density. The lighter ices could have been boiled away, concentrating its rocky core. The plot thickens when considering atmospheric escape. Even if Eris once harbored these compounds, its low gravity, just 2% of Earth's, makes retaining an atmosphere nearly impossible. Over billions of years, solar radiation could have gradually stripped away any nitrogen or carbon monoxide molecules that ventured into gaseous form. Pluto, with slightly stronger gravity and occasional atmospheric puffiness, might have held onto a fraction of its volatiles through this process, yet the most intriguing theory involves chemistry gone rogue. Methane dominates Eris's surface so completely that it might have actively suppressed other volatiles. In laboratory simulations, methane ice exposed to cosmic radiation can polymerize into long-chain hydrocarbons, effectively soaking up nearby nitrogen and carbon monoxide molecules like a sponge. Over eons, this could have scrubbed Eris's surface clean of competing compounds, leaving behind a methane monoculture. The missing volatiles aren't just an academic puzzle, they're a window into Eris's deepest past. Whether boiled away during a violent migration, stripped by solar winds, or chemically transformed beyond recognition, their absence tells a story of a world shaped by extremes. And until we taste its ice firsthand, this chemical whodunit will remain one of Eris's most compelling unsolved mysteries. Eris's orbit isn't just a static path through space, it's a cosmic tightrope walk, and scientists are still debating whether it's inching closer to instability with every passing millennium. Unlike most planets and dwarf planets whose orbits are locked in predictable rhythms, Eris's wildly elliptical and tilted trajectory raises a haunting question. Is this dance permanent, or is it slowly unraveling? The answer could rewrite the future of our solar system's outer reaches. Let's break down the forces at play. Gravity from the giant planets, especially Neptune, tugs at Eris constantly, like invisible strings trying to nudge it off course. Normally, objects in the Kuiper belt settle into stable resonances with Neptune, their orbits harmonizing over time. But Eris's path is so extreme that it skirts the edge of chaos. Some simulations suggest its orbit might oscillate over millions of years, wobbling between slightly more and less elliptical without ever fully destabilizing. Others paint a darker picture. Each close pass to Neptune's gravitational influence could steal a tiny fraction of Eris's momentum, nudging it incrementally toward the inner solar system, or flinging it deeper into interstellar space. The stakes are higher than they seem. If Eris's orbit is decaying, even minutely, it could become a rogue dwarf planet in the distant future, ejected from the Sun's grasp entirely. This wouldn't happen overnight. We're talking billions of years, but the process would scatter smaller Kuiper belt objects in its wake, sending icy debris spiraling inward where it might collide with planets or morph into comets. On the flip side, if Eris's orbit tightens, its gravitational influence could grow, potentially herding other distant worlds into new configurations. Imagine it as a celestial bulldozer, reshaping the solar system's fringe one gentle nudge at a time. The wild card in all this, Planet 9. If the hypothetical super-Earth lurking beyond Pluto exists, its gravity might be acting as a stabilizer, counteracting Neptune's tugs and locking Eris into an odd but enduring rhythm. Without Planet 9's influence, Eris's orbit could be far more fragile than we realize. Alternatively, Dysnomia, Eris's moon, might be the unsung hero here. Its gravitational pull, though slight, could act as an anchor, steadying Eris's path like a counterweight on a pendulum. For now, the data is frustratingly sparse. Tracking minuscule orbital shifts over decades is like watching an hour hand move in real time, but every new observation adds a piece to the puzzle. If Eris's aphelion, its farthest point from the Sun, has crept even a fraction closer over the past century, it could signal the start of a slow-motion cosmic unraveling. Or perhaps it's in perfect balance, a celestial oddity that'll outlast the Sun itself. One thing's certain, Eris isn't just drifting mindlessly through the dark. It's a ticking clock, and its orbit holds the time. Eris presents a magnetic puzzle, one that stands out starkly in a solar system where even small worlds often generate detectable fields. Take Pluto, for example. When New Horizons flew past it in 2015, instruments picked up signs of a tenuous interaction with solar wind, hinting at least a residual magnetic influence. Or consider Ceres, the asteroid belt's dwarf planet, which shows evidence of localized magnetism in its crust. Even Ganymede, Jupiter's moon, boasts its own internally generated field. Yet Eris, despite its size and density, remains stubbornly silent in magnetic surveys. For a world with so many active mysteries, this absence is itself a riddle waiting to be cracked. The most obvious explanation points to internal structure. Magnetic fields usually require three ingredients: a conductive fluid, motion within that fluid, and rotation. Earth's field springs from its molten iron core, churning like a dynamo as the planet spins. But Eris's interior, while dense, might lack the necessary heat to keep any metallic core liquid. Radioactive decay could theoretically provide warmth, but in a body this small, the heat likely bleeds away too quickly, leaving the core frozen solid. Without that conductive, moving material, no dynamo can form. Yet this raises another question. Why don't we at least detect a fossil field magnetism locked into Eris's crust from some ancient era when its core was active? Mars, for instance, retains patches of magnetized rock from its more dynamic past. If Eris once had a molten core, traces of that epoch should linger. The absence suggests one of two possibilities. Either Eris never hosted an internal dynamo at all, or some process, like global cryovolcanic resurfacing, has erased the evidence. Then there's the moon factor. Dysnomia's gravitational tug could, in theory, generate tidal heating within Eris, flexing its interior enough to sustain partial melting. Similar forces power the magnetic fields of Europa and Enceladus, but Dysnomia orbits too distantly to create significant friction, leaving Eris's interior too cold and stiff for tidal effects to matter. The most intriguing alternative, Eris might hide its magnetism beneath an insulating shell. If its subsurface ocean, if one exists, is sandwiched between layers of ultra-pure ice, even a sloshing conductive layer might not produce a detectable external field. Or perhaps its magnetic moment is simply too weak for current instruments to catch from Earth's distance. Whatever the reason, this magnetic silence speaks volumes. In a cosmos where magnetism often signals hidden activity, subsurface oceans, molten cores, or geological vigor, Eris's quiet defiance reminds us that some worlds guard their secrets more fiercely than others. And until we send a probe to listen up close, this particular mystery will remain frozen in time. Eris and Dysnomia don't just orbit each other, they blur the line between planet and moon, sparking a debate that could redefine how we classify cosmic partnerships. Most moons are mere satellites dwarfed by their parent planets, but Dysnomia's size relative to Eris, roughly 1/8 its diameter, makes this pair unusually balanced. For comparison, Earth's moon is just 1/4 our planet's size, while Pluto's largest moon, Charon, is half its diameter, nearly qualifying them as a binary system. So where does Eris fall on this cosmic scale? The evidence paints a tantalizingly ambiguous picture. The case for a binary system starts with their center of gravity. In a typical planet-moon duo, the larger body's gravity dominates so completely that both technically orbit a point deep within the planet itself. But when objects are close in mass, like Pluto and Charon, they revolve around a shared point between them, a telltale sign of a binary relationship. For Eris and Dysnomia, calculations place this barycenter just outside Eris's surface, but not as far into space as Pluto and Charon's. It's a gray zone, suggesting they're not quite a classic binary, but far more balanced than Earth and its moon. Then there's Dysnomia's formation. Binary systems often arise from colossal collisions that leave debris orbiting a shared center, think Pluto and Charon's violent birth. Dysnomia's composition, nearly identical to Eris's surface, supports a similar origin story. But here's the catch: Dysnomia's tight circular orbit feels more like a traditional moon's path than the wider, more erratic trajectories seen in most binary pairs. This odd combination collisional origin yet moon-like orbit leaves scientists split. Some argue that if Dysnomia had formed just slightly farther out, we'd unanimously call them twins. Others counter that its current position makes it undeniably a satellite regardless of history. The temperature of their relationship adds another layer. Binary systems typically exchange material. Think of Pluto's thin atmosphere drifting onto Charon. Yet Eris and Dysnomia show no such interaction. Eris's surface remains pristine methane, while Dysnomia is pitch black, suggesting no atmospheric bridge between them. This chemical disconnect feels more like a distant moon than an intimate binary partner. Perhaps the most compelling argument against binary status comes from their gravitational dance. True binaries like Pluto and Charon are tidally locked, always facing each other as they spin. Eris rotates every 26 hours, while Dysnomia completes an orbit every 16 days, their rhythms out of sync. This mismatch hints that Dysnomia hasn't fully tamed Eris's spin, leaving their partnership unbalanced. Yet the debate isn't just academic. If we classify them as binary, it implies Eris's formation was more chaotic than we thought, a world born from shattering violence rather than quiet accretion. It also reshapes how we search for dwarf planets. If binaries are common, our census of the Kuiper belt might be missing hidden twins. For now, Eris and Dysnomia linger in celestial limbo, too close to ignore the binary question, too distant to answer it definitively. And like so much about this enigmatic pair, the truth may lie somewhere between the categories we've created. Eris didn't just enter the solar system's ledger quietly, it kicked the door down, sparking a scientific controversy that still simmers today. When astronomers measured its size in 2005 and realized it rivaled Pluto, the revelation sent shockwaves through the International Astronomical Union. Overnight, the question wasn't just about adding a new planet, it was about redefining what a planet was. The old definition, vague and untested, suddenly crumbled under the weight of Eris's existence. If Pluto kept its planetary status, logic demanded Eris join the club, along with potentially dozens of other Kuiper belt objects. The solar system's tidy 9-planet model faced an existential crisis, forcing astronomers to confront an uncomfortable truth: their categories no longer fit the cosmos. The public backlash was swift and fierce. For many, Pluto's demotion felt like a personal loss, a celestial icon stripped of its title. School textbooks, museum displays, and even pop culture references had to be rewritten. The outrage wasn't just sentimental, it revealed how deeply astronomy intertwines with human identity. Pluto, named after the Roman god of the underworld, had become a cultural touchstone, appearing in everything from Disney cartoons to astrology charts. Eris, the usurper, bore the brunt of this frustration, often painted as the villain in the narrative. Yet among scientists, the reaction was more nuanced. Traditionalists dug in, arguing that historical precedent mattered as much as rigid definitions. Progressives saw an opportunity to refine taxonomy based on modern discoveries. The debate grew so heated that at the 2006 IU meeting, astronomers resorted to a vote, a rarity in a field normally governed by data, not democracy. What's often overlooked is how Eris exposed the flaws in our classification systems. Before its discovery, planets were loosely defined by size and orbit. But Eris forced a more precise criterion. Celestial bodies must clear their neighborhood of debris to qualify. Pluto and Eris, sharing orbits with icy rubble, failed this test. This new rule wasn't just academic nitpicking, it reflected a deeper understanding of how planetary systems form. Dominant worlds like Earth or Jupiter reshape their surroundings. Dwarf planets like Eris merely coexist with theirs. The controversy wasn't really about Pluto's worth. It was about recognizing that nature doesn't fit into tidy boxes. Yet the irony is rich. Eris, named for the goddess of discord, became a catalyst for scientific clarity. Its discovery didn't diminish Pluto's significance, it reframed our cosmic perspective. Dwarf planets weren't demotions, they were a new class of world, each with unique stories to tell. And while the public mourned Pluto's reclassification, astronomers celebrated. Eris had done more than challenge a definition. It had reminded us that science, like the universe, evolves. The old model wasn't wrong, it was incomplete, and in that incompleteness lay the thrill of discovery, the promise that even our most cherished truths might one day be rewritten by the next strange world lurking in the dark. Among the countless whispers of the cosmos, few are as puzzling as the faint radio signals allegedly traced to Eris's vicinity. These elusive emissions, sporadic bursts of static recorded by deep space monitoring arrays, defy easy categorization. They're not the steady hum of natural plasma waves or the predictable crackle of solar wind interacting with a magnetic field. Instead, they arrive in erratic clusters, each lasting mere milliseconds, with spectral fingerprints that don't match known astrophysical phenomena. Could these be the echoes of some unknown geological process or something far more extraordinary? The natural explanations are intriguing enough. On icy moons like Europa and Enceladus, charged particles interacting with subsurface saltwater can generate weak radio waves. If Eris harbors a hidden ocean, even a slushy, briny layer beneath its crust, similar interactions might occur. The dwarf planet's extreme seasons could play a role too. As methane ice sublimates during its rare close approaches to the sun, escaping gases might ionize, creating fleeting atmospheric currents that emit radio noise. Even its dark, cryptic patches could factor in. If those regions contain conductive materials like irradiated graphite, solar wind particles striking the surface might produce brief, localized bursts of electromagnetic interference. Yet the signal's irregular timing raises eyebrows. Natural processes tend to follow rhythmic patterns. Think of Jupiter's constant radio storms or pulsars' metronomic beats. Eris's emissions, by contrast, seem almost deliberate, not enough to suggest intelligence, but enough to make scientists double-check their instruments. The most tantalizing and controversial theory ties them to Dysnomia. As the moon orbits, its gravitational pull might flex Eris's icy shell, triggering cryovolcanic vents to open and close like cosmic radio transmitters. Imagine geysers of electrically charged slurry shooting into space, their plumes acting as natural antennas. Skeptics counter that these signals might not originate from Eris at all. The Kuiper belt teems with uncharted debris, microcomets, asteroid fragments, even rogue interstellar objects, any of which could generate static upon collision or disintegration. Worse, human-made interference remains a persistent ghost in the machine. Old satellites, spent rocket stages, or even terrestrial radio leakage can masquerade as deep space anomalies. Without a probe in situ to pinpoint the source, the signals linger in scientific limbo, tantalizing but unconfirmed, unexplained but not yet unexplainable. For now, these radio whispers remain one of Eris's most enigmatic loose threads. Whether artifacts of exotic geology, cosmic static, or something beyond our current understanding, they underscore a humbling truth. Even in our own solar backyard, the universe still transmits mysteries we're not equipped to decode. And until we listen more closely, Eris's radio silence, or lack thereof, will keep its secrets. Eris may be frozen in the outer solar system, but our ambition to reach it burns hotter than ever. While no mission currently carries its name on a launch manifest, scientists and engineers are already sketching blueprints for probes that could crack this dwarf planet's enigmas wide open. The technological hurdles are staggering, but the potential rewards could redefine our understanding of the Kuiper Belt's strangest resident. Picture this: a spacecraft smaller than a compact car but packed with cutting-edge instruments, hurtling toward a world 4 times farther than Pluto. New Horizons' groundbreaking flyby in 2015 proved such journeys are possible, but Eris presents even thornier challenges. At its average distance, sunlight is 900 times dimmer than Earth's, rendering solar panels nearly useless. Future missions would need nuclear power sources, like the plutonium-driven RTGs that fueled New Horizons, a scarce resource with geopolitical complexities. Communication delays would stretch to over 10 hours each way, forcing probes to make split-second decisions autonomously. And with Eris moving slower than a crawling toddler in its orbit, matching its trajectory requires precision engineering worthy of a cosmic ballet. Yet the scientific appetite for this venture is ravenous. Imagine spectrometers mapping Eris's surface chemistry in pixel-perfect detail, revealing whether those dark patches are organic sludge or cryovolcanic soot. A laser altimeter could scan the ridge zones millimeter by millimeter, hunting for telltale shifts that betray subsurface oceans. Even a simple camera might spot plumes erupting from fissures, direct evidence that this world isn't the frozen corpse we assumed. And let's not forget Dysnomia. A close flyby could determine if this moon shares Eris's density, or if it's a captured interloper with secrets of its own. The dream scenario: landing. Though Eris's gravity is just 2% of Earth's, a controlled touchdown isn't impossible. Think Philae's comet landing, but with years to plan the descent. A stationary lander could deploy a drill, melting through methane ice to analyze pristine layers beneath. Or it might listen for seismic tremors, using moonquakes triggered by Dysnomia's tug to map Eris's interior like a celestial ultrasound. The data would be revolutionary, offering our first ground truth from a classical Kuiper Belt object. Timelines remain hazy, but whispers at NASA and ESA suggest the 2035 to 2045 window could see such a mission take shape. Advances in ion propulsion, like the kind powering NASA's upcoming Dragonfly drone to Titan, might slash travel time from decades to under 15 years. Meanwhile, breakthroughs in miniaturization could pack multiple landers into a single spacecraft, creating a fleet of robotic geologists. What's truly at stake goes beyond one icy world. Eris is a time capsule from the solar system's violent adolescence, its composition and structure holding clues to how planets big and small assembled from cosmic rubble. A successful mission wouldn't just solve mysteries, it would teach us how to read the stories hidden in all the distant, frozen worlds waiting beyond. And with each passing year, as technology catches up to ambition, the question shifts from if to when. The era of Eris exploration isn't coming, it's already on the drawing board. Eris isn't just another frozen rock at the edge of the solar system, it's a wrench thrown into the gears of our cosmic models, forcing us to question how well we truly understand the story of our own celestial neighborhood. Every oddity about this dwarf planet, from its tilted orbit to its inexplicable reflectivity, acts like a piece of a puzzle that doesn't quite fit the picture we've spent centuries assembling. If the solar system's history were a book, Eris would be the footnote that demands an entire rewrite. Take the grand timeline of planetary formation. Conventional wisdom paints the Kuiper Belt as a quiet graveyard of icy leftovers, where objects like Pluto formed in place and slowly froze into relics. But Eris's density and composition scream something different, a world that might have been forged closer to the Sun, then violently ejected during Neptune's chaotic migration. Imagine a celestial game of pinball where planets hurled debris into the abyss, and Eris was one of the survivors. If true, this means the Kuiper belt isn't just a static museum of primordial ice. It's a dynamic scrapbook of the solar system's most turbulent era, with Eris as its most enigmatic page. Then there's the glaring inconsistency of its surface. Why does methane dominate here when nitrogen rules on Pluto? Why do some regions stay impossibly bright while others swallow light whole? These aren't just cosmetic differences, they hint at geological processes we haven't seen anywhere else. Europa and Enceladus taught us that icy moons can harbor hidden oceans, but Eris suggests dwarf planets might play by their own rules. Could its gleaming plains be evidence of an underground engine we don't yet understand? Or does its chemistry point to a formation story unlike any other world we've studied? And let's not forget the gravitational ripple effect. Eris's orbit doesn't just defy expectations, it might be sculpting the paths of other distant objects, whispering clues about the hypothetical planet 9. Every unexplained cluster of orbits in the scattered disk could be a breadcrumb leading back to Eris's influence, or to something even larger lurking in the dark. The more we study this dwarf planet, the more it feels like a key to unlocking secrets far beyond itself. The open questions pile up faster than answers. Is Eris's core still warm enough to fuel cryovolcanoes? Does its moon Dysnomia hold traces of a catastrophic collision? And most hauntingly, what else is out there waiting to append our theories once again? Eris reminds us that the solar system isn't a solved equation. It's a living, evolving mystery, with this icy rebel at the heart of the next great cosmic revelation. The only certainty, the more we learn, the stranger the truth will be. From its bizarre orbit to its missing craters, its unexplained brightness shifts to its silent magnetic field. Eris has spent nearly 2 decades rewriting the rulebook of planetary science. We've counted down 25 of its deepest enigmas, how it defies expectations with every measurement, how its chemistry contradicts the outer solar system's norms, even how it might be whispering gravitational secrets about unseen worlds. Yet with each mystery solved, 3 more seem to take its place. That's the beauty of Eris. It refuses to be just another icy relic. It's a cosmic provocateur, challenging our models, upending our assumptions, and proving that even in our own celestial backyard, discovery is far from over. The most thrilling part, this story isn't finished. Every year, new telescopes peer deeper into the Kuiper belt, and fresh missions are drafted to explore its frozen frontiers. Maybe one day, a probe will crack Eris's glare to map its hidden geology. Maybe we'll find geysers erupting from its plains or detect tremors hinting at oceans beneath the ice. Or maybe, just maybe, Eris will surprise us all with something no one predicted. That's the pulse of real science, not tidy answers but better questions. So keep looking up, keep wondering, because out there in the dark, Eris is still spinning, still hiding its secrets, still waiting for the next curious mind to pull at its threads. And if this journey through its mysteries has left you as captivated as we are, don't let it end here. Smash that like button if you're ready for the next chapter, subscribe to stay in the loop as new discoveries unfold, and drop your wildest Eris theories in the comments. Is it a rogue alien world? A time capsule from the solar system's birth? Your guess might just be the one that sparks tomorrow's breakthrough. The universe is stranger than fiction, and thanks to rebels like Eris, the best stories are still being written.